depending also on the size of the island. Or you can grow it vertically as such. For instance, you have in the down there, you have silver 111. You can grow it vertically. Also, such a system, you can have a superconducting transition. In this image, I show you just two different layers. One is terminated by the bits timer, and the other one by gallium tetrachloride. And you can see here in the insert, it is quite interesting spectroscopy, ubiquitously on the island as well. But something remarkable happened that the direction of these dimers, actually, they are deposited epitaxially. And since you have three of such directions that equivalent, sometimes you see the direction of these dimers, which also the direction of the anti-nodal order, they are taking this shape of these high symmetry axes. As a result, this antinodal particles may mix. So what we see here when we do the spectroscopy, instead of having this sharp, but instead we are getting flat bottom. This is basically because these particles somehow they smear their anisotropy, especially at high energy states. At low energy states, and because they are coming from different directions. And this is our depiction of this phenomena is like you have a flat bottom instead of the usual shape of the wave. So it's still the wave, but this flat bottom is coming from the mixing of the antinodal order. More striking feature is that when the dimers are not sufficient enough, in that case, the anion cannot find the dimer. And interestingly, in the beginning, they are like sporadic, as you can see in the image A, but little by little, the energy then develop into a chain. Interestingly, not dissipated, but rather spread out through the whole island. And with that, this is quite, of course, interesting. There's a well-defined magnetic chain, in fact, as I will show later, that are going through the superconductor. More importantly, we do not see any destruction of superconductivity in such a system. This is, I will show exactly why, but in general, we see that this mix is always there. And of course, under certain experimental conditions, you can always find its structure. So when you go to look at the phase, you see the usual superconductivity, you see some proximity effect, they disappear at 7 Kelvin. But it's always there, even on the chain, you don't see any variation, although slightly less than the stripes. The stripes are made of dimers, and they are the most conducting part of the lake. Now, when you go to high temperature phase, something interesting happens. So you start to see inelastic peaks coming up, and you start to see also so you can see, for example, the red curve here is taking at gallium tetrachloride side, while you see on the B side also similar dip, but in addition to it, some inelastic peaks. These inelastic peaks actually coincide very well with the phonon spectra of the Betz crystal. And interestingly, this structure actually exists at low temperature. None of these features you can see at low temperature, right? You see just superconducting. But above the superconducting transition, you see all inelastic peaks. You know that these are falling because their intensity increases with temperature as well. So finally, I come to the flat bend. So if we adjust the growth condition, instead of growing linear, we see the dimer, as you can see here, they start to meet each other and condense into primary units. And with that, they do it in such a way they form a Kagome lattice. And this Kagome lattice is unusual, actually, in the sense that it is robust at room temperature. Once it is formed, it usually forms roughly, wide range, roughly like 150 Kelvin. But once it is formed, it is so stable that even above, slightly above room temperature, is still stable, but it destroys completely around 70 Kelvin also, 70 Celsius. Interestingly, they are quite large. It can go up to 500 nanometer or so. I must say that it's very difficult actually to go to Kagome in other systems But this one is quite robust and quite large, so you can do also other spectroscopic techniques like ARPIS and so forth to study. But what's interesting about them is that they are frustrated in the sense that you definitely can include some magnetic transition in them and study also unconventional phenomena. Here I just demonstrated this fact briefly. So you see the bright red color here. These are basically molecules of gallium tetrachloride. They are embedded just right at the hollow site of the carbonyl lattice. And if you look at their states here, the bias, the I over dB, you see that they are bright, sharp features that are not spreading, and that is the absence of scattering in this energy range, and that's basically a result of flat band characteristics. This is some other work on CC as well. You can see this is also similar properties, but the carbonyl structure this is on a double layer, but it's also very, very small structure. It's like size of 10 nanometer or so, but we can produce it up to 500. And this is another feature of this crystal structure, that the whole has to be made of this material. You can make it empty, or you can fill it with molecular magnets and study, for example, spin liquid behavior and so forth. But the molecular magnets will be larger than 1 nanometer in size. This is another characteristics of this lattice, where again you see localization of guest states, in this case the gallium tetrachloride, and also the primer side. The states are not, the fluids that have maximum is relatively sharp, and there is no other feature in the other energy range. And of course, here you basically fill it totally with molecular magnets. And this would be a future work. Essentially, we are introducing magnetic species and study the behavior of spin liquids and other unconventional magnetism in the system. Finally, if you heat this crystal, what you get molecular wire, and this wire presumably antiferromagnet. This is you still have to check, but these bright spots are basically gallium tetrachloride, and the underlying feature here are made with structure. It's interesting to note that at the surface of silver, the magnetic order is slightly disturbed. So it's not, one needs to isolate it from the substrate in order to see magnetic ordering. But the fact that you can glue them into a wire is quite interesting. And finally, I come to conclusion. So I just showed you that when you glue the material in a different condition, you can end up with a different packaging geometry. And they can go from superconducting to wires to flat band. And you can also introduce magnetic ordering without destroying the crystal structure. So if you want to introduce, for example, topological phases or so, you don't have to worry about placing something over the superconductor, but rather you can implement it inside the superconductor. And that is to say, you do not destroy the translational order. The second thing is that the carbonyl lattices can be filled with radical anion, and this can be also gallium or iron tetrachloride, thus giving you an interesting way of looking at everything from organic perspective and well-defined system. So you don't have to worry about, let's say, doping level variation and so forth, as in case of, for example, copper. But here, if you decided to move to carbonyl lattice, you can perhaps study also unconventional superconductivity if you tune the system. The other thing is the mixed orientation, and also the proximity effect is clearly visible in this island. With that, I'd like to thank my collaborators, Joe and Kobayashi Sensei from Japan, Miyazaki Sensei in Toronto University, and Andrea Duarte and Stefan Krechner And Tanaka-san and Tokumoto-san, my former host in Japan, from Gensuken or Sansuken at the moment. And thank you very much for your attention.
Thank you.